Recording is rolling. It's Friday, August 19th. So a lot of guys just turned in this trigonometry page. Right? There was this lab side of it, and then this these twin triangles on this side. I had you guys pick 5 of those. Right now, I just pulled you guys, and tell you what, I'll give you guys the let's do similar deal for the idea for conceptual classes last class, which is if you feel completely good about what you did and turned into the grade tray, then awesome, you're good to go. I'll try to save a few minutes at the end of class today where I'll go back and do a little bit more practice, maybe do one more triangle example from each side of that page. And if you really need more time with that, like I could really use the weekend to go look at that again. That's a skill that you're going to need all throughout this year, is like breaking vectors and components. So that trigonometry, you're going to have to work your way around triangles. So tell you what, if you need the weekend to look at that a little bit more, you want to hold on to that page, then and just turn it in when I see you guys next week. That's fine. I won't count it late because this is a skill that I really want you guys to have. Right, and I'll take a few minutes in class today and do some more examples. Okay. So speaking of next week we're going to finally get into kinematic motion. I've got a lab lined up for you guys that involves Hot Wheels cars. So displacement, velocity, time. Acceleration is a rate change of velocity. It's like what's the rate that you're speeding up or slowing down. Okay. And I remember I've got this new equipment never used before, so we're going to get to do some things with this lab that it's never been done before. I'm not actually going to see you guys on Monday. Monday's going to be a weird day. Monday, you guys are going to be in your first period class for 3 periods worth, and then you're going to skip straight to 4th period. Okay, so that's going to work. So yeah, I won't even see you guys, but I'll figure that out. We'll make it happen. Okay. All right, then okay, you guys don't care about the AP stuff. So there's one last skill I want to get in before we really get rolling with everything else this year. So yeah, right about now, everybody's schedules are settling down. I usually want to take the first about week and a half to cover some essential skills, but if you just switch to this class, you'll be able to go back, catch the videos, catch up, and be all right. And here's the last skill we have to cover: dimensional analysis, which hopefully you guys are familiar with from chemistry. But let's go back to a review of that and say, hey, what's kind of a physics application of this? Okay. So let's start with say how many days are in 1 million seconds. Okay. So I'll give you guys a little time. See if you guys can solve that before I show you guys the answer, or walk you guys through the answer. 1 million seconds. How many days is that equivalent to? All right, if you could do that. Yeah, what you got, right? Ooh, I got something a little smarter than that. What do you guys see? 11.5 days. Ah, yeah, see, we got it. All right. So here's what we're gonna take that original value, 1 million seconds, pop it right here, 1 million, and then lowercase f to be seconds. You guys remember that from yesterday? Okay. Or if you like, you just do 10 to the power 6. All right, and then I'm going to do this method where I like the railroad tracks. Now, depending on who your chemistry teacher was, you may or may not be familiar with this exact model, but I'm going to use the railroad tracks. Okay, and these are essentially a bunch of fractions that are going to be multiplied together. Now, I know here's a good roadmap to solve this problem. Could you go seconds to minutes, minutes to hours, and then hours to days, convert? Okay, so we're going to do a bunch of unit conversions. Okay, I know there are 60 seconds in a minute, so I'm going to do this. I'm going to put the 60 down here. 60 seconds, okay, is equivalent to 1 minute. Okay, 60 seconds is equal to 1 minute, right? Now, here's the theory of why this conversion process works, like with the railroad track. That right there, that fraction, right? 1 minute is equivalent to 60 seconds. So what is anything divided by itself? 1. Yeah. So aren't we taking the original value and multiplying it by 1? Which means we're not really changing anything, but we are swapping out the units. Because look, the seconds cancel. So 1,000,000 divided by 60 represents the number of minutes, right? Right. Oh, so let's keep going. How many minutes in an hour? 60. Now, in this case, sometimes the number goes on top, sometimes bottom. Does the 60 go on top or on bottom? Bottom. 60 minutes in an hour. And you know it does because that would allow the minutes unit to cancel. And now we have hours on the board. Is that? But the question was how many days? So we still need one more step, which is going to be what? 24 hours. Yep, and that exactly goes in the bottom. 24 hours is equivalent to 1 day. Okay. So again, like the theory of why this works, you're just multiplying across times 1 times 1 times 1. Okay. But now all the units cancel except for days. Days is the only unit left on the board. So calculator time, I'm going to take 1,000,000. I could also call it 10 to the power 6. Okay. Times 1 times 1 times 1, right? And then divided by all the stuff on the bottom. The way I'm going to do it is divide by open parenthesis, and then just group all this together. 60 by 60 by 24. Okay. Let's see what this is. 11.57 days. All right. A little over a week and a half. 11.7 days. All right. Good. Next question. If you follow that, how many years is a billion seconds? Yeah, but yeah.
31.7 years.
Oh, Ryan got it. Yeah, 31.7 years. That's right. So it's like the same process we just did, but just one more step. Let's do this. There is 60 seconds and 1 minute. 60 minutes is equivalent to 1 hour. 24 hours in 1 day. And then about 365 days in a year. Sure, 366 days. So seconds, minutes, hours, days. The only unit left on the board is years, so this describes some number of years. Let's see how this works in the calculator. So a billion seconds divided by 60 by 60 by 24 by 365. That is indeed 31.7 years. Ooh, there's the difference between a million and a billion. Well, factor of 1,000, I guess, is the mathematically, but in terms of time, go from about a week and a half to like 30 something years. Woo! Let's do. You guys want to solve a pizza party?
Yeah.
Suppose you have to figure out how much you have to budget for pizza. You're gonna have a party, a bunch of friends over, and you want. I wonder how much I need to spend buying pizza. What are some things you think you'd have to know to answer that question? How many people? Let's say 14 people. You and 13 friends. What else do you have to know? Hey, how many slices per pizza? Let's say that there are 8 slices per pizza. That's a fraction, right? Okay. What else do you have to know? Cost per pizza. Let's go. I'm just copying from my notes here. Let's go $9 per pizza. Is that enough information, or do you still have to know one more thing?
How much each person has.
Exactly. How much is each person going to eat? So let's do an estimate. Let's say 4 slices per person. All right. You guys tell me, how much do you need to budget for this pizza party? All right, we figured it out. Yeah, you got it. Oh, no, no. Um, yeah, what did you get, Danny? Yeah, Danica got it. $63. All right, so I'm gonna start with the hard number. Notice that these three bottom numbers are like ratios or fractions, but the top number is just like a hard number. So normally how this works is you start with that. 14, I'll say like persons, people. Okay, and then we need to did things we did before, but now we're gonna somehow translate and get a number of dollars at the end of this. I do see one fraction that involves people. It's 4 slices per person. Should the 4 go on top or on bottom? Let's see. Here, hello both. How about this? 4 slices per person, because that's a fraction, right? Okay. Do you guys see the people's kind of cancel? So at this point in the railroad tracks story, we know how many total slices are being consumed. Okay. What ratio goes next?
8 slices per pizza.
8 slices per pizza. Now does the 8 go on top or bottom? So down here, 8 slices for every 1 pizza. Okay. Now we know how many total pizzas we need to buy. This does work out to be a whole number in case you think about that too. Okay. One more thing. Dollars per pizza. Now, does the number 9 go on top or on bottom? Top. Yeah, because it's $9 per 1 pizza. So there's only 1 unit on the board. Okay, so that's the budget. So let's do multiply across the top, 14 times 4 times 1 times 9, and then divide by, I see an 8 down here. That is indeed 63 is the number, and dollars is the unit. Now, the examples we've done so far have been conversions, which is probably what you mostly use dimensional analysis for in chemistry. Let's do a little twist on this. This next example is not strictly going to be conversion like the ones we've done so far, but it does use dimensional analysis, just a slightly different application. Suppose you fill up your gas tank and then you drive around, let's say 305 miles to the next gas station, and then you fill up your tank again. Let's suppose you spend, just make up some numbers on the fly here. Let's say $28 even filling up your tank, and that gasoline costs, let's go $3.90 per gallon. Right? Now, I want you guys to tell me, here's the question. What is the fuel efficiency of your car? The fuel efficiency. You know what you're doing, go ahead. If you're totally stuck, I'll give you guys a little hint here. Fuel efficiency. What is the unit for fuel efficiency? Miles per gallon. Can you somehow arrange those top 3 numbers to get the unit miles per gallon? Yeah, it might be. I haven't worked this out yet. Who thinks they know the answer? Yeah, what you guys see?
I got 42.5 miles per hour.
Well, that's what I'm getting to. That looks good. All right. So here's the way we're gonna go about this. You need miles per gallon, right? So we're gonna fit these numbers in such a way that you end up with those units. Miles is in the numerator. So do you think the 305 miles would probably go somewhere in the numerator? Let's go do that. 305 miles. Okay. Now again, this is not a unit conversion like the last few examples were, but what you can do is analyze the dimensional units. Okay? It's like putting together a puzzle, right? Putting all the puzzle pieces in place. You need gallons in the denominator. Hey, how about $3.90 per gallon? That would put gallons in the denominator, right? So I'm going to do $3.90 per gallon, right? So there's your miles and your gallons, but you got the dollars in there. That's not part of fuel efficiency. If only I could somehow divide out the $28, right? So let's put $28 down here, right? And then right, now you have exactly the units you need. Okay? So let's say what is 305 miles times 3.90 divided by 28. That is the number is 42 point something, and then well, go ahead, this. That is miles per gallon, right, or MPG, miles per gallon. There you go. Okay. Now, truth be told, I mean, that'll work. That is the answer. Sometimes this might fit into a formula, and then you can do something very similar, but you might be missing. Had this been a formula that had a coefficient of 1/2 or something, you would not have that information by you looking at unit analysis. Okay. But then in this case, this works perfectly fine. Okay. Let's do. I'm gonna give you guys let's up the challenge a little bit. Okay. One day, a few months from now, I'm going to give you guys a lab. We're going to take some mass, put it on a string, loop that string through a PVC pipe, and swing this whole thing around in a circle. Okay. And this is going to be held in check by a weight that's pulling it down right here. You guys can see that? PVC pipe. You guys ever swing a ball around on a circle? You feel some tension in the string? You guys feel that? So I'm going to have this mass up here. I'll call this M for mass as a variable, right? There's going to be some speed V, like V for velocity, but we'll just call it speed because it's moving in a circle. Okay? There's going to be some radial size R of the circle. And this weight that's hanging down over here, because remember the string is attached over here, providing some weight. I'll call that F for a force. Hey, do you think that force is providing the tension? You guys remember those hungry monkeys pulling the bananas? Right? There was like a tension force. I think this force in newtons is this tension in newtons. Okay. Now, force is measured. So as a variable, take a little table here. Variable unit. Force is measured in newtons, and 1 Newton is equivalent to 1 kilogram meter per second squared. The variable M mass is measured in kilograms. The variable R radius is measured in meters per second, and the variable V, velocity or speed in this case, I'm so sorry, guys. That's meters per second. Radius is meters. I'm being silly. Okay. Now, careful. This M is mass. This M is meters. Variable units. So careful with that. Okay. But just that clarification. Okay. You guys tell me, how can you solve for this force given these other 3 guys, right? This mass, this speed, this R. So we're going to put together a formula. So force equals, right, in some combination of these guys. I'll give you guys a hint. It's a fraction, so there's going to be some dividing going on. And also, you might have to square one of those variables. So something might be squared, right? It's a good challenge question. And if you follow the units, it'll lead you straight to the answer. Give you guys a minute here to solve that. There's some way you can multiply or divide these 3 guys, M, R, and V. There's some way to do that so that you get force. You might have to square one of those guys. Anyway, does anybody at this point think they might have a pretty good guess? Yeah, what do you think? Ken?
Is it gonna be meters per second squared times something? Like,
Alright, so the answer is just gonna be in terms of these three variables, something to do with M, R, and V. So something multiplied, something divided, something's being squared. Looking for a formula here. To it. Suppose you thought it was like, I'll give you guys a counterexample. Maybe something's wrong. Maybe you think it's force equals the mass squared times the radius divided by the speed, for example. Okay. Now you can use the units to check your work and see if this makes sense. Right, so we're going to say question mark, and the answer is no. By the way, this is That's it. So let's see, mass would be in kilograms. They do kilograms. I say that would be squared, right? Radius could be in meters. Speed could be in meters per second. Is this equal to newtons? Right? This top line is variables. This bottom line is all units. You guys see that? Okay. Well, I know 1 Newton is 1 kilogram meter per second squared. Okay. Is that equal to kilograms squared times, oh, does this meters cancel? And times 1/1 seconds. Is that kilogram squared seconds? Is that kilogram meter per second squared? No, that's totally wrong. So that didn't work. That didn't work, right? Oh, yeah, I think.
is the answer maybe like, the, would it be V squared times R over M?
Ooh, close. Okay. How about this? Okay. Now let me show you guys why that does work. Okay. mv squared over r. So force is that equal to mv squared over r. Let's try it out. So is in terms of units now, 1 Newton, is that equal to kilograms times meters per second collectively squared divided by meters, right? Let's see if that's true. Well, I know 1 Newton is 1 kilogram meter per second squared. Is that equal to, okay, I got kilograms. Well, it looks like kilograms is going to pop in place. So that's okay so far. Now this is meters squared per second squared, and then also divided by meters. Oh, and then 1 of the meters cancels. Yeah, that does work out. Kilogram meter per second squared is in fact kilogram meters per second squared. Bing! It checks out. So this formula works. Okay. Now, is that then the correct formula? Well, you wouldn't know exactly for sure. You could say proportion. This is what you actually could say at this point. You could say proportional. This is proportional to this. You would not know necessarily if there's like a 1/2 factor or something like that. Now, it turns out, spoil this, this actually is the exact correct answer. Right, so you guys will get that yourselves in a few months in the lab. But yeah, at least in terms of the units, that could be a candidate answer. But something like this would not be, but this would. Okay, you guys see that? See all these variables and units come together. Okay, all right. Let me throw one more at you guys, and actually this last one I'll just leave you guys as a challenge problem over the weekend. This won't be homework, but if you want a really good challenge problem to look at, where'd it go? Just out here. All right, so challenge problem. Suppose that the energy usage in the States is equal to 25,000 terawatt hours per year, where capital T tera is 10 to the power of 12. That's that guy right there. And also, let's have average solar flux be 400 watts per square meter. But let's have maximum solar flux. Like if it's really bright, sunny day outside, let's call that 1360 watts per square meter. So it's like, how bright does the sun shine? Oh, well, that's how you could quantify it. Here's maximum, here's like average, and it's day and night, it's cloudy, it's sunny. Let's say 1 kilometer is equal to 1,000 meters. Okay. And one more detail, let's say the efficiency of solar panels is 20%, which you guys know as a decimal, that's actually called 0.20. Right? Okay. So given those values, question is, what land area is required to power the USA on only solar? Okay. Now, answering this question, the kind of thought process is this is called a back of envelope calculation, which means we're making some simplifications, right? So there might be some engineering difficulties, maybe like that, like grid level storage, or maybe some other things, right? But just mathematically, there's enough numbers here where you can actually, on back of an envelope, do some dimensional analysis and come up with a land area. This would be in square kilometers. I'm looking for some number of square kilometers. Okay, so you at least have some idea. So there you go. There's a good challenge problem if you want something, good challenge problem over the weekend. All right. Here's where though, some of you guys are saying I might need a little more practice on this trigonometry. So here's what I do. Wait, anybody got any questions so far about dimensional analysis, anything? All right, so I'm gonna take the last few minutes of class here and I'll see if I can fit in one more of these with you guys and also one more of these. So if you need a little bit more practice on this. If you feel really good about what you turned into the gray tray, then you're good to go. If you really could benefit from holding this over the weekend and checking your work, then that's okay. You can turn it in next weekend, and I won't count late. Right. So let's see. I haven't done the Tesla, but let's do the Tesla triangle. Okay. So using the protractor. Okay. So if you're trying to get alpha and beta, remember I need 5 measurements, right? 2 angles on 3 sides, and then I'll do a bunch of calculations. So how do you measure what's the size of this wedge, the size of this angle, or the size of the angle? So I'm going to take this protractor, I'm going to take this node right here and park it right on this corner. By the way, in Google Classroom, there's some paper protractors. If you want to print this out, have access to this. I'm going to zero out this leg, and then this hypotenuse naturally runs through the angle. Okay, so that is right up there. See the size of that wedge? Looks like it's 68 degrees, I call it 68 degrees. That's for alpha, 68 degrees. Right. Or alternatively, you could do it this way. Now, if you do it this way, if you zero out the hypotenuse first, you see how this leg is way too short and doesn't even run through the protractor. So for that reason, what I'll do is I'll go ahead and extend this leg. I'll extrapolate it. You guys see that blue line? Great. So I can get this angle alpha going clockwise on the protractor instead of counterclockwise. Okay. That runs through. Oh, it's still 68. So the size of this wedge right here, 68 degrees. That really runs through 2 numbers. It also runs through the number 112. Okay. But guys, your alpha and your beta, those should add up to what ideally? 90 degrees. So shouldn't alpha and beta each be less than 90 degrees? So if you're ever getting anything over 90, you're probably reading the wrong number on the protractor. Okay. So just subtract from 180 is 182. Okay, alpha need to get beta. So let me park this node right in this quarter, zero out this leg, and the hypotenuse sweeps through. Looks like 20 something, like 22, about 22 degrees. 22 degrees. In fact, these two added together does add up to 90. If it's anywhere between 88 and 92, you're okay for science. When side C, ideally, like mathematically, it should be exactly 90 though. What is, see, 7.7, I'll call it, maybe 7.7 centimeters. I need side A. This looks like maybe 7 point, maybe 7.0, maybe I'll call it 7.0, 7.1, something like that. Okay, and then side B, if you also have Tesla triangle on your table, you should be getting numbers that are at least pretty close to what I'm getting. If it's off a tiny bit, it's perfectly fine. 2.8 maybe, somewhere there. Okay. All right, so there you go. I'm done with the measurements. Now I'm going to pull up this calculator and do these 6 calculations, right? 3 and 3. Okay. Now remember that dark rectangle that runs around these 4 cells and these 4 cells? Right? That's because there's 4 different perspectives on like the same side over and over. So I have a measured value for side A, but what does the calculation say? That C times sine alpha. Well, if you start with C, the hypotenuse, multiply by sine of alpha, that kicks over opposite of alpha, which is also side A. So that's a reference to side A, C times sine alpha. C is 7.7 centimeters, sine, now alpha and A, two totally different concepts, different units, don't mix those up. Alpha is 68 degrees. That is 7.13, I'll call it 7.1. Hey, that is extremely close to my measured value. So I'm probably on the right track. Okay, next one, C times cosine beta. Now cosine beta, that runs adjacent, that translates hypotenuse to adjacent leg, which is also side A. Let's do 7.7 centimeters. Cosine beta was 22 degrees. Yeah, it's also 7.1 centimeters. Next, square root C squared minus B squared. You guys remember that's reverse Pythagorean theorem? Right? So, look, Pythagorean theorem, did a little bit of algebra. It's also a perspective on side A. So let's do square root of 7.7 squared minus, this, here's your B, 2.8 centimeters being squared, 7.17. I should have been keeping another digit. What was this again? Oh, this calculator messed up. Well, okay. You guys get it? All right, these last three. C times sine of beta. Now C times sine beta that kicks over opposite of beta, which is side B. So let's try this out. 7.7 centimeters times sine of 22 degrees, 2.88 centimeters. My measured value was 2.8. That's really close. I'm happy. Next one, 7.7 centimeters times cosine of 68 degrees is also 2.88 centimeters. And finally, reverse Pythagorean theorem, square root of C squared minus A squared, 7.7 squared minus, here's your A, 7.0 squared. That comes out to 3.21. That's plenty close enough, right? 3.2, 2.8, that's kind of thing, okay? You guys get that? All right, so there's a third example. All right, how about, let's see what I can do here. So I can fit in one of these. How about number 5? Let's do number 5. All right, hey, if alpha is 24 degrees, what is beta? 90 minus that. Shouldn't these two add up to 90 degrees? I'm going to do 90 minus 24. Get 66 degrees, right? Z. If I give you the hypotenuse, isn't hypotenuse times sine of 24 this leg, and hypotenuse times cosine of 24 this leg? Right? I'll do it that way because that's the only way I can beat the bell. I'm going to do 14 centimeters. Let's do it right here on calculator. 14 centimeters hypotenuse multiplied by sine of 24 degrees that kicks over opposite to this leg. That's y. That's 5.69. I'll call it 5.7 centimeters. And then if I scroll up, scroll over, and replace the sine with cosine, boom, get the other leg. 12.7, that rounds to 12.8 centimeters. 12.7896. 12.8 centimeters. There you go. There's another one of those. Okay. All right, so remember, I'm recording all these. They're on Google Classroom. I'll upload this one in Google Classroom too. So you have 2 more examples there, plus the examples from the last few days. Yeah, really good skill to be able to use the protractor and also work your way around a triangle. All right, who's got any questions? All right, you guys have a great weekend.